Good day, calculus students. Today, approximate integration. The purpose of this unit is to show you a variety of ways of also approximating the area under a curve. So we're after the amount of area under this curve here, and the function that we are given is 1 over x, and we know that it's over the interval from 1 to 2. Now I could get an exact answer to this using the fundamental theorem, right? The exact area under this curve would be the integral from 1 to 2 of 1 over x. This would give us a natural log of x evaluated from 1 to 2, which gives us just natural log of 2. And natural log of 2 is about 0.693. We'll say roughly 0.693. Let's keep that in mind as we move forward with this unit. It's not always possible to be able to find an antiderivative of a function. Even though we've been learning lots of techniques up to this point, there are still functions out there for which we do not have a known antiderivative, so we can't use the fundamental theorem. So the purpose of this unit is to cover some ways to approximate the area under a curve in those cases where the fundamental theorem fails. Now, the methods we're going to use, though, we are going to use on this simple function for which we could use the fundamental theorem. Right? Everything I'm about to do for this particular example is sort of pointless because we were able to get the exact area right here pretty quickly, but this is simply to illustrate the methods. All right, the instructions here are to use 4 midpoint rectangles to approximate the area under the function over this interval. Now, 4 midpoint rectangles, what this means we're going to do is take this interval right here and make 4 equal length subintervals out of this. So there's the half point, the 1.5, the half of that, and the half of that. So we have 4 equal pieces. It's also a good idea to label these pieces. This would be 1.25, or if I wanted to use fractions, I would say 5/4. This one here is 3/2, or let's go with common fourths. So this would be 6/4. The one over here in decimal would be 1.75. That's the same thing as 7/4. And then, of course, you could think of 2 as 8/4. And you could think of 1 as 4/4. In fact, each of these gaps here is 1/4. And how do we get that? Well, we could take the entire gap from 1 to 2, which is 1, and then divide that by 4, right, to figure out how wide each subinterval is going to be. And we're going to use a delta x to represent how long each of these subintervals is. We'll call that delta x. Okay, the next thing we do is imagine 4 columns now. We're going to make rectangles out of these, but rectangles have flat tops, right, not these curving tops. You might recall doing left-hand sums and right-hand sums in Calculus 1, where if you look on one subinterval, so focus on this subinterval right here, this first rectangle, and you go to where the left side intersects the function, and you use that height, whatever it is, as the height of the whole rectangle. You make a rectangle like this. This is called doing a left-hand sum. Or if you were to use the where the right side of this subinterval intersects the function and use that retroactively as the height of a rectangle, right? And then so you would be, talking about this area here. The method we're going to do here, though, is called a midpoint rectangle. So what we're going to do is we're going to actually track down the middle of each of these intervals here. We're going to call these the 4 midpoints of the 4 subintervals. Notationally, I'll use a little m sub 1 to mean the first midpoint, little m sub 2 to mean the second midpoint, and little m sub 3 the third, and little m sub 4 the fourth. Now we want to figure out what these actual x coordinates are. Well, the way to find the midpoint of 2 numbers, so if I want to find the middle of 4/4 and 5/4, is to average them. So add 4/4 and 5/4, you get 9/4, but then cut that in 2, and you get 9/8. So the first midpoint has coordinates 9/8. Now add these two, we get 11/4 divided by 2, 11/8. Here we get 13/8, and here we get 15/8. Notice that to go from midpoint to midpoint, that this is still the same width as delta x. And so if you want to go from one midpoint to the next, you could just add the delta x, right? And the delta x was 1/4, or 2/8. So notice to go from 9/8, add 2/8, you get 11/8. Add 2/8, 13/8, add 2/8, 15/8, right? So there's a variety of ways to go about figuring out all of these midpoints. Okay, the next thing we want to do is plug 9/8 into the function, and we figure out what y coordinate you get. Then we use that as the height of the first rectangle. Now notice why this is advantageous, because where our rectangle is missing some, but then it has more than some over here. So we have both an over approximation and an under approximation combined into one rectangle, which is nice because that means that this midpoint rectangle is certainly going to be better than doing either a left endpoint rectangle or a right endpoint rectangle. Now the height of this first rectangle can be found by taking the 9/8, which is our first midpoint, and plugging it into the function. So we do f of 9/8. Now this particular function is simply we call this the reciprocal function. It's just, and so when I do f of 9/8, that really just means 1 over 9/8, which is the same thing as 8/9. So 8/9 is how tall that first rectangle is. All right, then if you were to repeat this process, you're going to get a bunch of different heights. This one here, this height of the second rectangle will be found by doing f of 11/8, which will give us 8/11. The next height will be f of 13/8, which will give us 8/13. And the final height will give us the reciprocal of 15/8, which is 8/15. These are the 4 heights of the 4 rectangles. And the width of each one is delta x. And delta x is going to be a quarter. And one way to find that is to take your overall interval and figure out how wide it is. So sometimes these are referred to as a and b as the interval. And so the general formula would be do the b minus the a, but then divide that by how many rectangles you're using. So divide that by 4. And sometimes this 4 will use an n to stand for how many rectangles you're using. So the general formula for finding delta x would be b minus a over n. And in this case, that would be 2 minus 1 over 4, or in other words, a quarter. All right, so now we're just going to add the areas of these 4 rectangles by hand, and we're going to get an answer. We're going to use a capital M to stand for doing a midpoint rectangle. Subscript will tell you how many. According to what we're seeing here, there's really just 4 rectangles here. You could say area 1 plus area 2 plus area 3. That's all we're doing, is just adding the areas of the 4 rectangles. To find the area of each one, you would do the delta x and multiply it by f of m1. So I'm writing generally here. The next one would be delta x times f of m sub 2. Notice though, as I keep writing this, you're going to see that each one of these is going to have a delta x. So I'm going to actually factor out the delta x to the front and just add the 4 heights. So the next height would be f of m sub 3 plus f of m sub 4. Now what you're seeing up here is a general formula for finding m sub n, where you're doing more and more rectangles. And you can see it being used specifically right here in the case of doing 4 rectangles. Okay, now let's keep pushing forward with this. M4 is the delta x we discovered was a quarter. The first height was by plugging in 9/8 into the function, and we got 8/9. The next height was by plugging in 11/8, and we got 8/11, etc. Then we got the next height was 8/13, and the final height of the rectangle was 8/15. Doing the rest by hand is kind of tedious. Getting a common denominator there is not very pleasant. So I went ahead and used a Desmos, add those 4 fractions, and then multiply by 1/4, 4,448, all over 6,435. Which is approximately 0.6912. Now notice how that compares to the exact answer, which was about 0.693. So we're a little bit of an underestimate here. All right, now the next part of this slide is to approximate the same area, but do 20 midpoint rectangles, then 50, and then 100, and use technology. So I'm going to do this using a pre-made Desmos file that I will wind up sharing with you. All right, the things you have control over is you can type in what function it is. The A and B here are sliders that you can drag around to different numbers. N is how many rectangles we're doing, and you can see how the more rectangles you have, the more refined our approximations get. So let's just park N at 4. The next little bits of this, you have to turn off or turn on the shading of whatever kind of method we're doing to approximate. For example, if we're doing left-handed rectangles, you would get the following image that you see here. And the sum is given right below the image. You see that left sum 0.759. Notice that if you're doing left hand sum, you're going to get an obvious overestimate of the area. And if I turn on the right and I want to turn off the red, this is doing right hand sums, and its area is an obvious underestimate. Let's turn that off and turn on the midpoints. And here's a representation of what we just drew by hand, and the midpoint sum is given below in green. We're going to learn something called trapezoids and Simpson's rule in just a moment, but for now let's go with just looking at the midpoints. This little thing that you can toggle on and off just hides those bars, and the reason that's helpful is when you do more and more rectangles, it starts to just look like a black image because there's so many black lines here. Don't worry about these folders here, right? If you open these folders, you're going to see all sorts of formulas. These are the formulas I use to do the programming. You don't have to worry about messing with that. Okay, now our instructions were to do the midpoint using 10 rectangles, but I'm just now realizing our notes didn't ask for 10, asked for 20, 50, and 100. 20 there, and there's using 20 midpoint rectangles. And we get 0.6930691, and then you can change this to 50 rectangles, And notice that you have to really zoom in to see all these little steps that are happening here. As should feel intuitive to you is that the more rectangles we use, the better our approximations are. So you expect to see the answers converging to the correct answer. And then the last one was to do 100 rectangles. Let me change that 50 to 100. And here's a midpoint sum of 0.69314406. All right, so moving those results to our work over here, M20 was approximately 0.69306991. Doing 50 midpoint rectangles gave us approximately 0.69313468. And doing 100 midpoint rectangles gave us approximately 0.69314406. Now up here we said the exact answer was natural log of 2, 0.6931471856. Okay, look at all of our answers so far in decimal forms. We have our midpoint 4, compare it to the exact answer, it's lower. But since our midpoints are getting more refined, we expect them to get closer to the exact answer, so they should go up. 20 midpoints, but notice it's technically lower than this one. Using 50, it's still less than natural log of 2, and even using 100 rectangles is going to be less. So all of our answers are underestimates, but they're getting closer and closer to the exact answer. Okay, let's move on to discussing the trapezoid rule. We're going to do the exact same function and region and approximate the answer, so we know the exact answer is natural log of 2. This says use 4 endpoint trapezoids, and there's a reason I call them endpoint trapezoids. The 4 means to break this interval up into 4 subintervals. It's good to determine all of these. We have 1, then we have add a quarter, so 5 quarters, add a quarter to that, 6 quarters, or 3 halves you could write, add a quarter to that, 7 quarters, add a quarter to that, takes us to 8 quarters or 2. In the case here, we're actually going to take the 2 endpoints of any one subinterval and make a straight line that connects them. Now notice because of the curvature of this function, it's concave up. When I do a secant line through a concave up curve, the secant line would be above the curved line because the curve was bending upwards. Anyway, what we wind up doing is 4 such trapezoids. From here, it's just, okay, how do I find the equation of a trapezoid? And then just repeat that for all of these and get all the trapezoids. Another realization to make, though, is that if I were to take the left-hand sum, which is high, and the right-hand sum, which is low, and average them, I would get the trapezoid area. The tall rectangle averaged with this shorter rectangle would give you perfectly in the middle. And so if I just connect these endpoints with a straight line and cut off this top part, then I just average the left and right hand sums. And the formula that I'm going to use is a formula that comes from that way of thinking. You just average the left and right hand sums. And it's going to wind up producing a formula that looks like this. Still going to have a delta x that's found the same way. You do 2 minus 1 over the 4, the b minus a over n. So we get a quarter is the delta x. That's how wide each trapezoid is. For notation-wise, down here below, the a is sometimes referred to as the x naught. And then we count them up from there. So this would be x sub 1, this would be x sub 2, x sub 3, and then the final endpoint would be x sub 4. So notice that the final subscript matches the number of trapezoids. And the way to add up all these trapezoid areas is to do the following. So in this case, the trapezoid using 4 trapezoids will be delta x over 2. Then we do f of x naught. Then we're going to do double and do f of x sub 1, double f of x sub 2. We're going to double all the interior y coordinates. Double f of x sub 3, and we keep this up until we get to the last one, but the last one we just do 1 copy. Notice that we see a total of 5 y coordinates being used, and the interior ones are all doubled, but the exterior starting and ending ones are single copies. This is a result of adding the left-hand sum and the right-hand sums together, which all the middle ones get used twice, so when you add them together you double, and then you divide by 2 to do an average. That's why this division by 2 is out here. Alright, so specifically in this case here, we get 4 trapezoids, delta x was a quarter, so we have a quarter divided by 2. We're going to plug in 1 into the function. Now keep in mind the function is still 1 over x, so you have to invert the x coordinates to get the y coordinates. When you invert 1, you get 1. Then we're going to double. Now plug in x1, plug in 5/4 into the function, which means invert it, so we get 4/5. Plus double, plug in x2. x2 is right here, 6/4. Plug that into the function, you get 4/6. Or you can say 2/3, plus 2. Shift gears to where the x3 is. It's right here. It's 7/4. Invert it is 4/7. And then the last x of 4 is just this 2. plug that in, which means invert 2, we get 1/2, but we don't need to double that 1/2. And this over here in the front, right here, that's just going to be 1/8. I'm going to reach for a calculator here because getting a common denominator is not going to be pleasant. Again, we wind up getting 1,171 all over 1,680, which winds up being approximately 0.6970. Notice that's more, right? The exact area was natural log 2, about 0.693. And that should make sense because the trapezoids were higher. Now we're going to do technology to get the other ones here. When you do 20 trapezoids, you'll get 0.69330338. When you do 50 trapezoids, you're going to get approximately 0.69317218. And when you do 100 trapezoids, you're going to get approximately 0.69315343. Notice that all of our approximations here, all 4 of these, are all over estimates. But we're getting closer and closer to the exact answer the more trapezoids I use. Let's go to the software and show what's happening here and how to use this. Left side menu, I don't need to change much. Let me change this back down to 4. Let's turn off the midpoint visual and switch to the trapezoid visual. And let's turn on the little black lines for now. So here's 4 trapezoids. And let me zoom in and you can see that in fact each trapezoid is too much. And if we let's go ahead and jump this to 20. Now we have 20 trapezoids. And to the naked eye, it looks like we pretty much have an exact answer. But you really have to zoom in to see, right, that each trapezoid is in fact more than the area we're looking for. And that is because the curve was concave up. And when you, like I said earlier, when you draw a secant line through a concave up curve, the secant line is higher than the curve. And then just look to the orange answer, trapezoid rule, to get sums for the trapezoids. Let's do the next rule called Simpson's rule. Okay, Simpson's rule. We're going to use n equals 4 with Simpson's rule to approximate the area under this function over the same interval. We're going to do this without using technology. When you use Simpson's rule, what's actually happening here is if n is equal to 4, then you still want to think of this interval being broken up into 4 subintervals. And what Simpson's rule is going to actually pair off these columns. It's going to use these first 2 columns right here and the 3 points where it intersects the curve above. So this point, and this point. And it's actually going to do a parabolic arch that passes through those 3 points. And the parabolic arch is going to look very similar to the non-parabolic function. 1 over x is not a parabola. But we're going to connect these 3 dots with a parabolic arch, or I'll just call it parabola 1. Then we're going to pair off with the second 2 columns. Use this point here again, use this point and then make a parabolic arch through those 3 points. And this would be parabola 2. Now, since we're approximating the area under a curve by using curves, using parabolas, you might expect to have a little bit more precision. Once again, the 1 here will be our x naught. The 5/4 that's right here will be our x1. The 6/4 that's here will be our x2. The 7/4 that's here will be our x3, and then the 2 will be our x4. And the general formula I've written to use to do this, to find the area under these parabolic arches, is given right here. Now let me show you what it looks like specifically for s sub 4. So Simpson's rule using 4 subintervals. It's going to be delta x divided by 3. All right, so we're going to use the first x coordinate and just do 1 copy of that y coordinate. So f of x naught, but only 1 copy of it. Then we start this 4, 2, 4, 2, etc. up and end on 4, alternating coefficients until we get to the second to last. And then the very last term will have a 1 coefficient again. So we're going to have 4 copies of plugging in x1. Then we're going to have 2 copies of using x2, so plug x2 into the function. Then we're going to have 4 copies of using x sub 3. And now we're down to the last one, and the last one will just be 1 copy of f of x sub 4. All right, so delta x was a quarter, and a quarter divided by 3 is a 12th. F of x naught, so x naught is the 1, plug that into the function. Invert 1, you get 1 still, plus 4 times. Plug 5/4 into the function, invert it, you get 4/5, plus 2 times. Plug x2 into the function. Remember that was a 3/2 or 6/4, and invert it, so you get 4/6 or 2/3, plus 4 times, and now let's plug in x sub 3. Right, x sub 3 is the 7/4, plug that into the function, and you're going to get 4/7. And then we do 1 copy of plugging in 2. Right, x sub 4 is 2 right there. Plug that into the function, you get 1/2, and just do 1 copy of that. All right, and then when you reach for the calculator and turn this all into just one big fraction, you get 1,747 divided by 2,520, which is approximately equal to 0.69325. Okay, so there's our exact answer again. Notice how, of all the methods, this one got us closest to the answer with the least amount of work. Now, if I were to do S sub 20, I'd wind up getting 0.69314,737. When I do S sub 50, I get approximately 0.69314,719. And when I do S sub 100, I get approximately 0.69314,718. And we're getting closer and closer and closer to the exact answer. And it seems like Simpson's rule each step along the way gave us better approximations than either the trapezoid or the midpoint rules did. Now, bear in mind that when you do S sub 100 and you get this calculation, if I were to ask you how many parabolic arches were used to get to this answer, the answer is 50. Right? So remember, the subintervals get paired off. And so if you have 4 subintervals, you only had 2 parabolic arches. If you have 100 subintervals, you have 50 parabolic arches that you're working with to approximate the area under the curve. Change n back to 4, hide the trapezoid visual, and show the Simpsons visual. The shading looks pretty good to the naked eye here, but if you do zoom in, you will eventually notice that the parabolic arch and the function itself are not the same. Okay, let's move on to something called recovering distance from speed. Now, hopefully we're all comfortable with the notion that if you're going a constant speed and you go that speed for a certain amount of time, then you just have to multiply time times your speed and you get the distance traveled. Right? Just as a simple example, if you're going 3 feet every second, but then I say, hey, do that for 5 seconds, right? If you do the arithmetic of units, seconds cancel, 3 times 5 is 15, and you would say you go 15 feet. Well, sometimes you can model distance with area. For example, let me draw a little rectangle here, and let's say that the x-axis is representing changes in time and the y-axis represents speeds. So let's say that the elapsed amount of time was 5 seconds here, and the speed that we're saying that we were going was 3 feet per second. And so we're going to use area of a rectangle to model distance traveled, because the amount of area inside this rectangle here is 15 units. But what are those units? Well, they would be feet in this case. When we first learn area, we think of it as, a square foot. Like here's a foot by a foot. And how much space does that take up? But we're going to be using area to represent things that are not area, right? Because the amount of area here is 15, but the units are feet, not square feet. So we're using area to represent things that have nothing to do with two-dimensional space. Okay, so we have this table of data. At different times, we know the speed of an object, and the goal is to use midpoint, trapezoid, and Simpson's rules to approximate the total distance traveled by that object. And I'm going to make a little number line here. We're going to start it at 1 and end it at 25. How many subintervals can I create out of this? Well, we have 1, 2, 3, 4, 5, 6 subintervals. So I'll cut this in half and then in thirds. So there's 6 subintervals. The times are 5, 9, 13, 17. Notice we're just adding 4 seconds to go from piece to piece. So we are being consistent in how our times are increasing. They're always increasing by 4 seconds. Okay, now the speeds are these numbers 2, 3, 5. Speed is going to be represented by this axis, and time is the horizontal axis. And all we have is data. We have 1, 2 is a point. We have, and this won't be to scale, but we'll have 5, 3, and we can see that as I do this, I'm just getting higher and higher speeds. Even though I don't know the curve necessarily that's connecting these points, we don't need to know that because we can just use the data itself to effectively do the same thing that we were doing up here, where you did know the curve, and we used the curve to find the data. But now we just have the data without the curve. And let's do midpoints first. If I wanted to do midpoints, and I have all these subintervals, you would need to know the midpoint of 1 and 5, average them. 1 and 5 averaged is 3. But we don't have data for 3. So I can't do an M6 here, because I don't have the data for the midpoints of these 6 subintervals. But what I can do is pretend like we only have 3 subintervals. And now I can use the 5 as the first midpoint, the 13 as the second midpoint, and the 21 as the third midpoint. And so whatever those heights are, I'm going to make my rectangles out of those heights. Okay, so when I do this, the delta x is actually, because I'm only doing 3, the delta x is from 1 to 9. So delta x is 8 in this case. Let's calculate M3, which is delta x times f of 5 plus f of 13 plus f of 21. Now when you plug 5 into this function, that's like just saying, hey, here's the input, right below is the output. That point right there was a height 3. So the height of the first rectangle, if you will, is 3. and we use the outputs are the speeds. We're going to use those three outputs to correspond with the inputs of 5, 13, and 21. And so we get m3 is equal to delta x was 8, f of 5 was 3 feet per second, f of 13 was 8 feet per second, and f of 21 was 18 feet per second. The unit of that 8 is seconds, and these units are all feet per second. So when you add them up, you have feet per second. So you're really doing a time times a speed. That's why you're getting a distance out of this. And anyway, using M3, we wind up getting 232 feet. I could not do M6, remember, because if I tried to do 6 subintervals, I would need data for the midpoints of those subintervals, and we don't have that data. However, when I do trapezoid, so here's our number line again. And again, we have our speeds are getting more and more as we go left to right. I can definitely do trapezoids using all of this data. Right, so I can actually have 6 subintervals because it's easy to make trapezoids right out of these 6 pieces. I don't need to know the midpoints to do this. So we can do trapezoid 6. Keep in mind that the first coordinate is x0, and then x1, then x2, and there should be x6 out of this because we had 6 subintervals. It's going to be delta x, and our delta x is now not as much as it was for doing M3. Delta x is the width of each subinterval, because we have more subintervals. Delta x is just 4 this time. And then you're going to do f of 1 plus, and then you double all the middle ones. So f of 5, I won't write them all down, ... double up to f of 21, and then do 1 copy of f of 25. Right, all the interior outputs get doubled. Oh, and I forgot to do delta x divided by 2. That's part of the formula. So T6 is delta x is 4, divide that by 2 is 2. Plug 1 into this function is 2. These are all the outputs for all the different times. So a single copy of that one, and then double all of the interior ones, and then a single copy of that one essentially is what's happening here. So we're going to double the 3, we're going to double the 5, we're going to double the 8, we're going to double the 12, we're going to double the 18, and then a single copy of the 28. And when I do all of this work, I wind up getting the following approximation, 244 feet. Right? Compare that to our midpoint 3 approximation. And then finally, the Simpson's rule uses all this same data. We can use S6 again because we need only these endpoints of the subintervals. We use them all, so we can just do S6 on this. It's going to be delta x, which is 4, divided by 3. So delta x divided by 3. And then it's similar to trapezoid from here, except that the coefficients are, 1 of these, 4 of those, 2 of those, 4 of these, 2 of those, 4 of those, and then 1 of those again. So we have some 4 coefficients thrown in the mix, not just 2 coefficients. Anyway, we have 1, 2, and we have 4 3s, 2 5s, 4 8s, 2 12s, 4 18s, and then only 1 copy of 28. And when I do this calculation, I get that S6 gives us an approximation of 240 feet. I should mention, going back here to Simpson's rule, that because we pair off the subintervals, you need the n to be an even number. Otherwise, you won't be able to pair them off. Notice what happens if I come over here and I change the n to 5. Notice no shading happens, even though I have it set to shade the Simpson's rule. And notice the Simpson's rule formula result. Underneath the image, it says undefined. But if you want to use Simpson's rule and get a visual and get an answer, make sure n is even, because it pairs them off to make n halves parabolic arches. Okay, so here we were able to approximate how far the object went using 3 different techniques, and given the data that we had, I guess it's fairly safe to say that the one maybe you should use with the most confidence is Simpson's rule. Simpson's rule will be the most accurate in general of all of these rules. Okay, one last slide. Given the curvature of a function, I want to talk about how to predict the ordering of your approximating techniques. So we have L, R, M, and T. Let's not bother throwing S in here. Let's just compare the left, right, midpoint, and trapezoids. And let's let a letter A stand for the exact area. So given these different shapes, we can say, okay, what's larger, using left-hand sums or finding the exact area? And let's pretend we're analyzing one subinterval. All right, there's 4 different curvatures that can happen with a function. You have decreasing and bending downwards, so concave down. You have a decreasing but concave up. This was the shape that we've been working with, the 1 over x. You have increasing concave down, and you have increasing concave up. And assuming that curvature remains intact through that subinterval, doesn't do anything like this, that has multiple concavities. And let's go with some colors to represent orange for the trapezoid. The green will be using the midpoint, and then a few other colors here. Let's say the right endpoints are using blue, and the left endpoints will be red. I want to talk a little bit about this midpoint sum real fast. If you're split this subinterval right here perfectly in half, figure out where the function hits the midpoint and then make a rectangle out of this. And the area of that rectangle would be the midpoint. If you were to leave this point fixed, but rotate that line, you would make trapezoids. So imagine I take the midpoint, I tilt the top so that the top is now at an angle, and I make a trapezoid out of this. Well, because we're using the midpoint, this excess equals exactly this deficit. In other words, the resulting trapezoid, which looks more like this, has the exact same area, right, as the original rectangle, provided that we pivoted around the midpoint here. So it's possible to think of midpoint sums as trapezoid sums because you can rotate the top of this rectangle without changing the area. And if you rotate it to the point where you're effectively doing the tangent line, it would look like this. So the amount of area underneath this trapezoid, and let's call this a midpoint tangent trapezoid and not an endpoint trapezoid, right? The difference being that when I'm talking about an endpoint trapezoid, I would grab the endpoints of where the subinterval hits the function and make a trapezoid out of that. That would be an endpoint trapezoid. Well, it's the ability to rethink midpoint sums, which are rectangles, but as midpoint tangent trapezoids, that's going to allow us to compare and determine whether the midpoint rule would give us an over or underestimate compared to the trapezoid. So from this image alone, you can already see our ranking. We'll put the exact area in the middle, right? That's the amount of area that's underneath the curve. So the exact area under the curve. Well, the area underneath the green trapezoid is too much. So the midpoint sum would be more than the area under the curve. But the area under the orange trapezoid, the endpoint trapezoid, the classic trapezoid method uses the endpoints, that area is too little. So the trapezoid would err on this side. The right-hand sum uses the right side where this intersects, but makes a rectangle out of that. And then it says, okay, what's the amount of area of that rectangle? So this rectangle right here, what's that area? And you can see that's also an underestimate, and it's also going to be lower than the trapezoid. Okay, so in this case here, we get the right endpoint is the worst approximation as far as an underestimate. Whereas the left, we would find where the left side hits the function, make a rectangle out of that, and then do how much area is underneath that. That's going to be an overestimate. And it's going to turn out that midpoint sums are better than left-rights. And so the left endpoint approach is going to be the highest of the overestimates. Now, in general, midpoints and trapezoids will be on the opposite sides of the exact answer. So if midpoint's an overestimate, trapezoid will be an underestimate. Yet midpoints and trapezoids are both better than right and lefts. Okay, and this next one, if you're decreasing concave down, you have a midpoint there, make a midpoint trapezoid tangent, then do your classic endpoint trapezoid. Let's do a left-hand rectangle would be there, and a right-sided rectangle would be here. And our ordering on this one will be let's put the exact answer right in the middle. The trapezoid is too much. Underneath the orange is too much. Underneath the green is too little, and that's a midpoint. And then the red, which is the left, is the most, and it's an overestimate. And the blue, which is the right endpoint, is the worst, the lowest. Compare these two. When the graph was decreasing, the rights were always the worst underestimates, and the lefts were always the worst overestimates. But the role of T and M flip-flopped. M went from being an overestimate to being an underestimate because of the concavity. That had to do with the concavity. The trapezoid used to be an underestimate, but now it's an overestimate. Again, that has to deal with the concavity. Now the midpoint sum, find the midpoint and do a trapezoid using a tangent line through the midpoint. Do the endpoint trapezoids, that's the classic trapezoid will be there. The right endpoint is going to be an overestimate now, and the left endpoint, using the left endpoint, is going to be an underestimate. So we have exact answer. An overestimate will be midpoint, and an overestimate on that would be the right endpoint. Underestimate of this would be a trapezoid, and an underestimate of that would be, a worse underestimate would be left. So now that the function is increasing, that's where you now have left as a gross underestimate and right as a gross overestimate. But because we are concave down, means that the T and M will be on the same sides of A as when you were decreasing concave down, right? So TAM, TAM. And then in the final case, midpoint tangent line trapezoid, make an endpoint to endpoint trapezoid. Our right side is an overestimate, and using our left side is an underestimate. So in this case here, we expect L and R to be in the same positioning as in the previous increasing case. And because we're now concave up, we expect the t's and m's to be the same as they were in the concave up decreasing. The midpoint is going to be an underestimate. Trapezoid will be an overestimate. So the monotonicity, which is a word for saying whether the function's increasing or decreasing, and the concavity of a curve, if those are known, then you can make predictions about whether the methods that you're using will be under or overestimates of each other.